All right, last little bit, 14.4, the hydrolysis of water via acid and base salts. We're going to talk about what this whole salts thing means in a little bit, but let's just talk about what the idea of the hydrolysis of water is. Again, if I have a water molecule and it can be somehow broken apart by a substance, so if I introduce a base to it, right, if this is an anion and I introduce it and it's going to grab onto, that is going to create a bond with that H, and that H is going to go back over there. We end up with OH minus and HA. So what we have essentially done is, well, I guess we have broken water, we have hydrolyzed water. And so we'll start with anions, because I just did start with anions, but again, the reactions of anions with water are as shown above. The idea of hydrolysis is we can react these things with water and we end up with a product. And we're actually going to come back here. I probably should have not given myself as much space here, but that's the idea for the reactions of anions with water. And actually, we're going to come right back up here because I want to look at the reactions of cations with water. Cations are going to work kind of the same way. The cations, the best example that I can give is here's an iron, and it's always, all right. So first of all, when I have some cation dissolved in water, so if I have an iron dissolved in water, when I write this out, Fe 3+ aqueous, because I've written this before, some version of this, sodium plus in water. What it doesn't look like is it's not just this sphere of iron just kind of cruising around in water. What really happens is this iron, what it really looks like is it's surrounded by this solvation shell of water molecules. So it has 1, 2, 3, 4, 5, 6 water molecules around it. And because this has that really positive charge, it is pulling the electron density toward it. So you can see that it pulls the electron density toward it. And so now what we have is, again, the oxygen is pulling the electrons away from the hydrogen, and the iron is positively charged, so it's pulling that negative charge to it. And so what we end up with is these positively charged protons. And so you have a water come through, and the water is going to come through and it's going to snag one of those and yank it off and go off into wherever it goes. So what we have is the end result of this is you have an iron that had 5 waters, plus now it also has an OH attached to it and an H3O plus. So what it has done is this is acidic because it produces H3O plus. And so if we actually look at the Kas, what we see is we do in fact see that they can, as the charge increases, we see an increase in the acidity, okay? And we see that by actual experimentation. Group 1, we do not expect to see it be acidic. It's not. Group 2 is not acidic either, very slightly. But zinc and aluminum, +3 and +2 and +3, are absolutely acidic of these hydrated salts. So here's the idea. When we are talking about salts, first of all, let's define what a salt is, as we always have to. A salt is simply 2 anions, 2 ions together. A cation, which you know is positive, and an anion, which is negative, and they're bound together. And what we're going to do is we're going to analyze them separately, and then we're going to look at their pH. Okay, so the idea here is, all right, they're going to have different pHs based on the ion acid base character. So if I take a thing of water and I drop some salt in, I'm getting a bunch of positive ions and a bunch of negative ions, and they're interacting with water. And ultimately what I want to know is it acidic? Is it basic? Or is it neutral? Okay. And let me show you how this is going to work. So we're going to start with our typical example. NaCl. So first of all, you're going to do this in multiple stages. And I want you to do this every single time you do one of these, and your life will be significantly simpler. Okay, so I'm going to break it into its two ions, because when I drop this into solution, I am going to end up with Na plus and Cl minus in solution. So I'm going to highlight this right here. This is what is in solution. Okay, so whatever is affecting the pH, it's the highlighted portion there. So do you know if Na plus is strong, weak, or negligible acid or base? We don't typically know these. So what we're going to do is we're going to say, all right, let's just take, because I don't know the ions, but what I do know is I can say, all right, I can add OH minus to this. What is NaOH? And I can do the same thing for, I can add H plus. So we're going to add the two parts of water, right? So if those two things, OH minus gets added to the cation and H plus gets added to the anion, and this becomes HCl. So now we take a look at this. So these are the conjugates. So NaOH, strong, so is an acid or base. We know that this is a base. Strong, weak, or negligible. NaOH is a strong base. Okay, so if NaOH is a strong base, what does that mean about its conjugate? So this is the strong base, this is the conjugate, right? So what is Na's conjugate strength? So if NaOH is a strong base, that means Na plus is negligible. It is a negligible acid. What does that mean? Sodium is not going to affect pH. So we expect it to remain neutral so far. What about HCl? Well, we know that that's an acid because the H plus, is it part of the strong acids? Yes, HCl is. HCl is a strong acid. So if HCl is a strong acid, that means Cl minus, its conjugate, is a negligible base. Because it's negligible, both of these things in solution are negligible, we expect the pH, these two things together, we expect the pH to be neutral. Okay, we don't need to predict what the exact pH is. We can figure out, I can show you how to do that if you need to, but remember, strong leads to a negligible conjugate, just like a weak leads to a weak conjugate. Okay. Okay. Let's take a look at another example. Let's take a look at KF. KF. Yeah, let's start with KF. And actually, I'll give you two examples. You should pause and you do it. Yeah, and then COBr2. So pause and break them into their ions. So I'm going to do that right now. K plus F minus. Actually, I'm just going to focus on this one, but I'll do this first. CO2 plus and Br minus. So we're just going to focus on this one to start. So I broke it into its ions. So what's in solution? Again, this is what's in solution. What are its conjugates? This becomes KOH. This becomes HF. KOH is a strong base, therefore this is negligible. Doesn't affect pH. Again, highlighted as what's in solution, right? HF is a weak acid. if HF is a weak acid, that means F minus is a weak base. Remember, weak becomes weak. Okay. So if I have a negligible substance, negligible ion, and a weak base in solution, what do I expect the pH to be? Well, we expect that the pH from these two, we expect the pH to be basic or slightly basic because we have the weak base of the F minus present. Okay, makes sense? All right, let's take a look at these. Cobalt becomes COOH2 and bromine becomes HBr. Again, this is what's in solution. So cobalt hydroxide. This is a weak base. Remember, it's not group 1. It's not the heavy hydroxides. It is considered a weak base. Therefore, this must be considered a weak acid. All metals are considered, all non-group 1, group 2 are considered weak. Any conjugates of non-weak bases are going to be weak acids. Okay. HBr is part of the strong acid list, and that means that Br minus is a negligible, and therefore those right there, the pH is going to be acidic. Okay, so that's the idea. So now I'm going to give you a bunch and we're going to do these in class together. So let's do NH4Cl. Let's do calcium carbonate. Let's do FeNO3. What else? Do I have some more? Sure. We're going to do MgCl2. We'll do let's do barium nitrite. And let's do NH4F. So tell me if those are acidic, basic, or neutral based on how they can hydrolyze water. All right, great. I think that's pretty much it for the chapter. We're going to get into more complex stuff, including buffers, which was supposed to be this chapter, but we pushed it to the next one, along with KSP. But very interesting stuff to come.